thank you. Thank you for being here at this session. We're about to watch, this is a real treat. So our speakers are Isaac McClure and Hail Kim. They also come from Gungahlin College in Canberra, like a previous speaker. And I won't say anything else about their talk. Please, Isaac and Hail.
Yes, thank you. So for me and Hail, we got interested in computer vision as part of our studies last semester, and then we started moving on. We had to do a project for school. And I was particularly interested in feature detection, and Hail was interested in using two cameras to find distance. And so this seemed like a really good project and really fun to combine those two different things. What the gun does is it finds people using the left camera, and then using both cameras, it finds their range, and then it directs a servo motor through an Arduino to point the gun at the person if they're in range. Yeah, as I said, we just chose to do this because it looked like fun to us. It took a fair bit of effort to get to where it is now, but we're just happy that it works at all. Yeah. Before I talk about any of the stuff that we did, I'd really like to recognize that we relied on many libraries from Python, and most especially OpenCV. And it was the fact that these are so easy to use in Python and easy to import, and that's why we could do the project at all, really. So mostly we relied on OpenCV for everything. But yeah. So now we're going to jump straight into a demonstration, because that's the fun part, and hope that it works. That one? Yeah, sorry. Okay. Can we hold up, see if you drag it. That's bad. Okay.
That's bad.
How did you change it before?
No, it was already on.
Yeah, okay. It was Windows P, right?
Oh, there we go.
Okay, so as you can, yes. Yeah. So, yeah, it's found him and it's tracking on. Then he's kind of, it's pretty trigger happy. I'm concerned about what it's aiming at right now, but besides the point. Yes, as you can see, it's tracking and giving us the angle and the person that it's found. If he moves a bit closer and further away, it might drop out. It tends to being able to see the entire person, and then it will find smaller things and call them people. So, yeah, that's basically how it works. It's fun. Go again if everyone wants. Ooh, there we go.
That's not good.
Okay, it seems to have, yeah, the camera kind of got plugged out. That's fine. Cool. Yeah, it sounds like something's in the barrel. Oh god, that's not going to go well.
It's definitely looking at me. Do they have ammo in there?
Yeah, not anymore.
Okay.
Okay. Cool. For some reason, the thing just went down. Why is what the fuck? Oh, it was one of those. Just I didn't plug it in and see what happens.
Well.
That's not good. For some reason it closes up. It was okay.
Stuff down the bottom.
Yeah.
No, you need to drag the window across.
Oh, okay. Cool.
So you make a new tab, not drag the tab out. Yeah, do you want to do that?
Just go from there. Thank you so much.
Sorry.
Cool.
Oh, can we make the present view?
That's easy. Is your mic on? This is the good way to start. Oh wait, we have the old one. Cool. How did I mess it up this badly? This was in case that didn't work.
There we go.
Cool.
Pull it up for you.
Thank you so much.
And then we go like that. Oh. There we go.
Cool. So thank you for sticking with us. There you go. Yeah, that's also interesting, isn't it? But yeah, that was the backup in case the demonstration didn't go to plan, but it seems to have actually worked, thankfully. These are some results from the hotel we were staying at last night. As you can see, the detector isn't perfect, and sometimes it finds other things and calls some people, but and moving forward and back tends to cause issues as well. But it was really easy to plug this in from HOG. We just had to play with a couple parameters. Its only main issues were that if you tune it to be fast, it becomes very inaccurate, and if you tune it to be accurate, it becomes very slow. But that's just a trade-off you always have to make. I'd imagine if you were trying to do this on a Raspberry Pi or like an integrated circuit, that could throw some major spanners in the work, but doing it on a laptop, it seems to run all right. So I'm going to try to talk a little bit technically about how the histogram of oriented gradients feature and pedestrian detection works. And hope that goes well. So feature detection is essentially the art of finding a unique and distinctive part of an image and describing it in a way that's smaller than the size of the data will be smaller than the image itself, because that's big. And also, if you were to find that same feature in a different image where the lighting or there's some noise or the scale or rotation has changed a little bit, the way you're describing it will be very similar so that you can find it again. So yeah, as I said, the detection we used is histogram of oriented gradients, which is very descriptive. How you calculate this is you go to each pixel in the image that you're using, and you apply a kernel, or a mask, I guess, and you use this to calculate a vertical and horizontal gradient. So the values for each pixel will be dependent on the color values of the pixels next to it. Some implementation use the greatest of the three color channels in order to use a value, and some of them convert the image to grayscale. So there's only one image, there's only one value to deal with at all. The idea is that if you have a corner or an edge, you'll get a really steep color gradient, and that'll make for a better feature. Once you've got those, you can combine them using Pythagoras and trig so that you have an oriented gradient. Normally you have unsigned, so you only have between 0 and 180 rather than signed. That's basically because you don't care if it's going left or right or up and down, as long as you know that it's going up, like it's vertically or horizontal. It doesn't matter which way. And it's easier to deal with only half of them. So once we've got an oriented gradient for each pixel, we can send that into a histogram. And essentially, we get the magnitude of each gradient and put it in a bin depending on the orientation of the gradient. If the orientation falls between two categories, you'd split it up. So if it was 60, for example, we'd put half of the magnitude into the 40 category and half of it into the 80 category. Once we've got all of those histograms, we group them into groups of 4 and normalize them. Normalizing helps with making it lighting invariant, so that if it was in a dark image and you had a same object in a lighter image, you'd get a similar histogram, and it wouldn't completely throw you off. As you can see, each of the histograms is in more than one of these blocks of 4. To be honest, I'm not exactly sure why we do that, but I can tell you that it is better if you do it. Yep, and then once we've got that, we send this giant vector, which is just adding all of those into one, and you send it off to the support vector machine classifier, which will hopefully tell you if you have a person or if you don't have a person. And that's how our cameras were finding people. But I will tell you about how we found the range.
So in our project, the HOG detector finds pedestrians, which are essentially our targets to shoot at. And the turret needs to decide which one of its targets to shoot, and we decide to make it shoot the closest one. Now the turret needs to determine how far its targets are in order to shoot the closest one. Since a regular computer with a single camera isn't able to do that, we're using 2 cameras. This technique of finding depth is called computer stereo vision. Essentially, it creates depth perception because an object appears at different locations in the images taken by 2 cameras in distance. This is also how our eyes create depth perception. Looking at an object with just one eye will be different when looking at it with the other eye. According to computer vision terminology, this difference is called disparity. To find the disparity, the corresponding 3D point has to be found on both images. This will be done using the orb detector and BF matcher from the OpenCV library. This technique is responsible for finding the target's distances to allow the turret to shoot the closest target. The disparity is bigger when it's closer to the cameras and smaller when it's further. This creates depth perception, allowing the computer to see distance. This is a simple example of disparity. The red dot represents a 3D point, and the squares represent images taken from 2 cameras in distance. Even though the cameras are seeing the same point, it shifts between the images due to the distance between the cameras. The disparity can also be seen with our eyes. Focusing on a finger right in front of us will make the object further away look as if they're shifting. Now that we have decided to create depth perception using disparity, the corresponding 3D object has to be found on both images. This is where the feature detecting and matching algorithms are used. Fortunately, OpenCV library includes those. In our project, I've used oriented fast and rotated brief for feature detection and brute force matcher for matching those features. Firstly, I found all the features on both images using the orb detector, and then I matched them with the BF matcher. Since the matcher just matches points with just same descriptors that we got from the orb detector, it often gave wrong matches. So I sorted these points so I can just work with the good points. Then I used the disparities of those points within the targets boxes we got from the HOG detector earlier to calculate distances of them. That allows the turret to shoot the closest target.
So what we did was essentially bringing together a whole bunch of other things and strapping it into our project in a somewhat haphazard fashion, as you can see. Yeah, we have just a Nerf gun mounted on a servo motor, which an Arduino controls. The Arduino talks to the laptop through the serial port, and that gets commands from a Python program, which is using OpenCV to, but yeah, it's using OpenCV to try find people in images from 2 cameras.
But making this was easier said than done. There was a number of challenges we have faced during this project in relation to both software and hardware. The first and the biggest challenge was making the HOG detector work properly. Since it was an unfamiliar algorithm for us, it took some time to make it detect humans properly. It required a lot of research and to understand how it worked and modify its parameters to improve the performance. When we tested the detection on a still image, it was fine, but when we started working with real-time video, it was very slow. We had to reduce its detection accuracy in order to make it faster while still keeping the detection working. We could achieve this by balancing wind stride and scale parameters. And finding this balance was mostly done by trial and error.
Yeah, our lack of knowledge about the hardware that we were using hindered our sort of progress with this project, and it ran us into a lot of issues. Initially, I had attempted to use a pneumatic ping pong ball cannon that I'd made for a different project, instead of a Nerf gun, but there was some issues with that, not the least of which is that it looked a little bit like a pipe bomb. But our lack of knowledge about the Arduino and soldering and general electronics also kind of hurt us, but it provided us an opportunity to learn as we went. So it was pretty good in that sense that we had to learn and we had to problem solve, which is, I guess, what this is all really about.
Besides having troubles to build the actual body, it was also problematic to set the Nerf gun on the body. It was mostly because the gun is heavy, therefore the servo motor couldn't support the weight. So we decided to set the gun on a bearing and attach a pole to the servo motor so it doesn't take as much weight. However, even then, the force of the gun spinning around was unscrewing it from the shaft that connects to the servo, so we superglued some more woods to keep it in place. The turret itself also moved when the gun turned, so the solution was to throw some weights on top, as you can see right there. The camera shaking while the gun was another problem because it made the program crash. Although I haven't figured out what the actual reason to cause this is, the closest thing I could think of was the BF matcher from OpenCV not being able to handle rapid change of images. So the solution to this was separating the cameras from the frame that holds the gun, which of course stopped the cameras from shaking. After all those solutions, the gun is now able to turn without making the turret fall over or breaking the servo motor.
Another big issue we had was that we really wanted to keep the budget as low as possible. Where this hit us, and we probably should have spent a little more, was on the cameras. We managed to scab these Logitech webcams for $18 each, but the cost was a 53-degree field of view, which means that really the camera can only shoot 27.5 degrees on either side. So ideally, if we were going to redo this project, I'd probably get new cameras and maybe get infrared runs and try to train my own classifier to work with that, but that would be a bit of a project. Basically, I had most of the stuff already sitting around. People call me a hoarder, but it seems to pay off sometimes. So the only things I actually had to buy were the gun, the cameras, and the servo. What this project was mostly about for us was learning, and I think we've really achieved that goal. I've learned a lot about using Python and OpenCV and how accessible that software is becoming for everyone to use. Like even me, and how we don't have a whole lot of a background in computer science yet, but we've managed to strap this together, and I think that's really cool because I think you're going to see it pop up in the world around you a lot more now that that's possible. We learned skills in other areas like electronics and woodworking, but obviously that still needs a little bit of work. But most importantly, I learned some things about project management, and that nothing's ever easy, and that's okay. And if you smash your head against the wall enough times, you'll eventually get there.
Yeah, honestly, I was really amazed how I could use all the required libraries so easily on Python. Doing a project like this wasn't something I've ever done before, so I've learned how to manage a project. I realized that putting too many hours into something at once and doing nothing for the next few hours is not the best thing to do. This project opened me opportunities to dive into new areas such as embedded systems and communication protocols, which we're using serial communication right now. And I would say that this was such a valuable experience for both of us. And that concludes our presentation, and we're happy to answer any questions.
We have 10 minutes for questions, so please keep them short and keep them questions, but keep them coming. Okay.
Great talk, and yeah, glad it's pointing that way. The computer vision portion of it, the examples that you were showing, both the hallway there and shooting against that wall, they were both a case of person wearing black standing in front of white screen or white wall. Have you done any experimentation to see how well those approaches work when the background is messy or obscured or moving or anything like that?
There's a little bit, if I find that backup video. You'll see in the second part of this video that it's shooting at me in my basement. I look pretty dead in this video, and that's because it was like 2 a.m. But there's a whole bunch of stuff, and it was finding some of the stuff on the wall, and also this bar stool happened to be in the back corner at the time, or another bus will like it, and it was finding that as a person sometimes. And that was where we were having problems with the detection accuracy, because we wanted to speed it up because the frame rate was getting really, really bad. But that was the balance we had to take. And I think, having good areas is something that really helps. Like if you see the bed frame on the left, that was getting shot fairly regularly.
Looks like it could be trouble.
Yeah.
I'm going to break the rule about questions to point out that that stool is this stool. It's traveled all the way from Canberra to be here today. Any questions? Yes?
How easy was it for you to figure out that OpenCV was the right solution?
It was very well documented, so not very difficult, but understanding the concept is the hard part rather than actually using it.
I'd use OpenCV professionally for similar sorts of things, not shooting people, by the way, but target selection. I'm interested in your choice of the HOG for finding people. Did you try the HOG Cascade face detector? And if you did, any comments on comparison of speeds?
I didn't, and that, for the most part, that was because when you Google pedestrian detection, that's what comes up, and that just went straight in. I was like, if it finds a pedestrian, that's basically the same thing, right? I read very briefly about the face detector you're talking about. I don't really know how it works. I'm not sure if it would help as much because it's not really aiming for people's faces, it's more aiming for the body, but yeah. Yeah.
So I have a question about the cameras. You've said that the field of the width of field bothered you. What about the speed? Did you find any trouble with the latency of acquiring images, or did you find that that didn't bother you?
Not as much as the field of view, but it affected a little bit because it was quite slow just by looking at the videos. So to work with it real time, it wasn't great.
I think the reason it didn't bother us a whole lot is because the software was slower than the input of the cameras. So maybe if we had really good software, that would be something we need to look at improving next.
There's one at the back. There's that from the back. Come forward.
So you were talking about the trade-off between accuracy and speed. How would you... What's an approach to solve that? Is it a case of you need faster hardware in the processing, or is it a limitation of the algorithm?
I think it's a bit of both. Obviously, if you have good enough hardware, you can kind of ignore the speed issues. But because I didn't write the algorithm myself, and because we've used it from there, I'm not sure if I'm in a real position to comment on the actual limitation of the algorithm. But I think there it gets to a point where, you probably can't improve both too much. I hope that answered your question. I know it wasn't too great.
A question that's almost, can we have more of a demo? The depth perception, can you actually show us that in action? So there are two people in front of the turret and it does pick one based on who's closer?
We can try.
While they set that up, I'm going to wait with our question so they can devote to the...
Is it already loaded?
We need to change the headset.
Oh yeah, do you want to do that? Yeah, that's good.
For those watching the video at home, we are setting up the demo as requested by the attendee.
That's pretty good.
Oh, gotcha.
Maybe it's a little bit too efficient. So if you go back a little bit.
Yeah.
Okay, it wants to shoot us both, I think, is the issue right now.
It's not even fighting Isaac, so
Yeah.
just stand a bit further back. It's definitely looking at him.
Yeah. No, it's definitely stuck on you. So right now, I don't think the range detection is really. It just wants to shoot everything. It's a bit of a problem, really. We were gonna think of naming it, and the first name that I thought of was a collateral damage, but my teacher came up with a possibly better one, which is misfire.
So while we go to the final question, how many times have you seen RoboCop each?
Actually, never.
Same here. I haven't seen it at all.
Hello. Just wondering, how did you figure out the power requirements for the? I imagine it's a air compressor inside the gun, and I came in late. Sorry.
Yeah, that's okay.
And did you need a relay to toggle the power for that circuit?
Yeah.
Or is there?
The bit of electrical tape at the back here is holding on the relay. That it uses. It's like, you know, tennis ball cannons. They've got like the two wheels that spin, and you push a tennis ball through the middle. And shoots. It does that same sort of thing. So there's like a little motor here, and then two bigger motors there, and it just pushes them into that. But that was all part of the Nerf gun, and that was what was great about cannibalizing it. Was that I basically just ripped out the switch in the middle and hooked it up to the relay.
We do have time for one more question. Who was, I think you were there first.
So you've used an algorithm that's specifically designed to detect pedestrians. Have you considered testing it and to see if it works against aliens?
Can't say it crossed my mind.
That's all the time we had, and I think we should thank Isaac and Hyle. Thank you so much.